Okay. All right. Let me just make sure our stream is set up and running. Oh, heck yeah, it's working.
So
Okay.
I start linear in the middle.
Yeah. Okay. Stream is up and running. And then let's make sure. Let's make sure this is working. Oops. Okay. Works. That works. Okay. So I just put hour timer on here.
Okay.
So
It's counting down for an hour.
it's gonna count down now. Okay. So just so you have like, all right.
It should be done before an hour.
Okay. Do you want the mic?
No, I don't. I'll stand up.
Okay.
Are you ready?
I'm ready. Yeah. Let's hang on.
All right, we're gonna start. All right, welcome to the Mechatronics presentation. I'm Alex.
And I'm Parker.
Yeah, and we're going to basically talk about how to design, build very general, broad, and then we're going to go through some of the slides kind of quickly, some of the more like general information slides, and then we'll have a bunch of examples which will ask you questions and you'll give us your answers.
We'll dive a little deeper.
Yeah, we'll go a bit deeper into the examples, and then at the end we have a design game where we have basically a skeleton block diagram, and we'll ask you to fill in the block diagram and put in the arrows. So
Yeah.
I'll send that to you after the presentation.
And the idea with these slides is it's kind of like a reference. There's going to be a ton of information in it. You're not going to necessarily learn everything. Some stuff will be like super obvious to some people. Some stuff will be novel to some people. So it's kind of very broad, a lot of detail, but we'll use this as a reference you can always look at later. So we might breeze over some stuff. We'll kind of keep engaged though. We'll ask you if you're like, this is too fast, this is too slow. So just let us know. And we'll answer questions during the presentation too. Because we have like an hour. So we can kind of go overflow to your
Yeah. Cool. Yeah, so like I said, I'm Alex. I'm a third year PhD student at CU, and I'm a member of the Animal Inspired Movement and Robotics Lab, and I have a mechanical engineering background.
And I'm Parker McDonald, and I'm a fourth year PhD student in the same lab as Alex. My background is electrical engineering, so that's together. We combine us two, you get mechatronics. And we kind of work on some kind of cool stuff in the lab, mostly insect scale robotic systems. So this is a project that Alex and I are working on together, which is build fully untethered, the first fully untethered, long duration, long term, unconnected flying insect scale system. It's quite a challenge, so we're not there yet, but the core of power autonomy and a small scale insect. And then another project that I'm working on, kind of stuff that goes on the lab, is building this kind of cockroach antenna inspired tactile sensor. And so a lot of stuff we do is like using a femtosecond laser. We use kind of Kapton and polyamide and carbon fiber to make stack laminates that we cut up with our laser and heat press, things like that. So that's kind of the different projects we work on in a nutshell.
Yeah, but we won't really be talking about that.
Yeah, yeah. Forget what we just said.
Or general robotics. But yeah, so today we'll be talking about what is mechatronics, how to design a robot, and then we'll have our game at the end. So kind of already learned that. So first, what is mechatronics? So I like to think of mechatronics as kind of the intersection of mechanical engineering, electrical engineering, controls, and computer engineering. So we'll be touching on each of these things during the presentation. All right, so mechatronics subsystems. So we have mechanical. So if you're going to build like some kind of robotic arm like this, you need the mechanical subsystem. So that's like the arm itself. And then you have the electrical. So hopefully some of you went to the PCB design workshop yesterday. You'll need a PCB and you'll need to route those signals throughout the arm to send information to the motors. You have controls. So sort of like the brain of the robot. How are you going to move? How do the different joint angles move to different parts of the design space, basically? And then you have software. So this is like what the robot is actually going to do, like what task it's going to perform. And with that, you can create some very complicated things. So this arm is doing some interesting task. I don't know.
We don't know what it's doing.
Something cool.
Yeah. Seems cool.
All right. So how do we build a robot? So the first thing that you're going to want to do is set your goals or requirements. So this is basically like, what do you want the robot to do? What can it do? What can it not do? where is it going to operate? So operating like underwater is very different than a Roomba, which is going to operate just on the floor in your house. You have to define what success is and what failure is. So for some robots, a 99% success rate might be great, but for some robots, that might be terrible. So knowing kind of how good you have to be is very important.
If you're mowing a lawn versus doing, heart surgery, there might be a different percentage of failure that's acceptable.
Exactly. You'll probably want to set a project timeline. You'll have a budget, and you'll want some technical specifications. So how big your robot's going to be, how much power it's going to use, how much materials it's going to use. And so by defining all these things before you start designing, that's super important because without any of these things, you just kind of get lost in the design process. Oh,
Safety.
Safety, yeah.
Whatever.
Safety, but
Yeah.
that's also very. All right, so robot workflow and the subsystem. So this is the workflow that you go to for building a robot. So we already kind of set our goals and requirements. The next step would be to select components and design the mechanics. So what the robot's going to look like, kind of what stuff we're going to buy, and then a big kind of task here. So this is like the kind of bulk of your design. So you want to select what kind of motors or actuators you're going to use, what kind of drivers you're going to use to drive those motors, the sensors that you're going to use, very important, any control algorithms that you're going to use, and the task algorithm. So this is like what the robot's going to do, like whatever tasks it needs to do. And then the mechanical design as well. And then once you're done with this kind of stuff, then you're going to go on and select a processor, a controller, and your power architecture. So a lot of the time people kind of lump these in with the whole design process, and that can be okay. But if you want to sort of like optimize what kind of controllers or what kind of power you're going to use, you're going to want to select all of these things first and then calculate how much information you need to be passing through your robot, how much power you're going to be using, and then select these things.
And there's other ways to do this too. Like
Yes.
you don't have to follow this exact timeline and kind of design flow,
Yeah.
but this is one option to design a robot.
Exactly. Yeah, so once you're done with that, you'll move on to prototyping, very important to test different things out, see what works, see what doesn't work, because you'll almost never get a design working on the first try. And then, right, from prototyping, you go back, redesign anything that needs to be redesigned, go back to prototyping, and then once you're happy enough, whatever you define success to be, then you can complete your final design. Okay, so moving on to, we're going to be talking about different kind of subsystems, components of robots. So we'll start with actuators and motors. So I'm going to talk about kind of four main motors that you'll see in your typical robot. So the first is a brush DC motor. And this is pretty much like the default motor. So has a wide variety of sizes, operates at a wide variety of voltages, typically high speed. And these are good to use if you want something that's cheap, if you want something that's wide variety, and they're also pretty easy to control. However, the brushes can wear down over time and they can overheat. So yeah, that's a brush DC motor. Then you have brushless DC motors, which are basically the fancier, higher efficiency version of brush DC motors. So also wide variety of sizes and voltages and speeds, but they're more expensive and more efficient than a brushed DC motor, and a bit more complicated to control as well. Then we have a servo motor, which is typically a DC motor with like an encoder or some sort of like reduction on it. So this is a pretty common servo motor. You can see the gear reduction in here. And so these are pretty nice. Also have a wide variety, pretty efficient, and they have high torque at high speed. And there's also two types, important to note. So there's a positional and a continuous servo motor. So continuous can continuously rotate, and positional typically goes from like 0 to 180 degrees and has really great position feedback built in. So if you need a high precision, then that's good to use.
And you don't have to do anything outside of it. Like you don't have to think, really. It does the thinking for you.
Yeah, the controls is very easy for a servo motor. Moving on to a stepper motor. So these work pretty differently than the previous two, and we'll talk about that in the motor driver section. And they're really good at positioning. so high precision positioning. That's why they're typically used in 3D printers, stuff like that. And they have low torque at high speed, but typically high torque at low speed, different from a DC motor, so you don't have to gear them down, which is nice. And then, of course, there's millions of other actuators out there. So AC motors, typically higher power, piezoelectrics. I'm sure you've heard that's what we use in our robots. Hydraulic actuators, that's what they use on the Boston Dynamics humanoid robot. Hazel actuators from Keplinger's lab, and of course many more. All right, so I'm gonna go through this super quick, but feel free to reference back to this at some point.
Or if
But
anyone wants us to slow down, just say
yes,
like
that's
I would
true.
like a little more detail on that, so we can go back.
Yeah, so this is basically a decision tree that I made for how you would select a motor. Yes, I think of them as being pretty much the same thing. I guess like I would say a motor is a subset of actuators. So motor, I think of as being like rotating. So like a stepper motor, DC motor, AC motor, those are all motors, but they're also actuators. But like a piezoelectric actuator,
Yeah.
that's not a motor because it just bends.
I think the actuators are basically anything that generate motion, or movement in your design, and that can be motors, it can be electrics, it can be hydraulics. So like it can be a really wide, like linear servos, things that move linearly, things that spin, like any sort of thing like that, I would call an actuator. So anything that moves you in the world is an actuator.
Yeah. I think it's just imprecise use of language. They're both, I would say a servo motor and a stepper motor are both good at high precision positioning. So let me click through this little decision tree. So basically, like this is kind of how you would select a motor if you knew you wanted to use like a stepper, or if you wanted to use a motor, not like some other kind of actuator. So going to your question, if you want precise precision control, we'll go to this branch. And then let's say we do want continuous rotation. Yes. And then you can see the two motors that you can choose are a continuous rotation servo or a stepper motor. So these both have nicely like built-in ways to get high precision position.
And like one other thing to think about is so yes, a servo and a stepper motor, you can do position control with both of them. Servos are generally like a lot cheaper.
Yeah.
It's less repeatable. Like you don't see 3D printers using servo motors for position control generally. I've never seen one. But a stepper motor is like precision at like micron level. It's repeatable. So if you tell it to go to the same location, it's going to do it every time. But it's not done through feedback internally. It's done just through the mechanism of how it's designed. And we'll talk about kind of like how it's actually controlled internally. But stepper motors are generally a lot more expensive and they can get hot too. Like you're constantly using a lot of power when they're just holding a position. So there's other trade-offs to think about, but yeah, like for example, a lot of robotic arms you see in factories, those will use stepper motors. But the GIF that you saw in Alex's was like a servo motor, but that was more of like a toy. So like generally cheaper things like fixed wing aircraft will use servo motors. They're pretty light too. So there's a lot of trade-offs with size and weight and precision. So it really comes down to your specific application, what you need it to do. Ari, did you have a question or? Um, don't. No.
Okay. Okay. So now we have an example. So for those who don't know, this is the Husky robot. So Sean's lab used that in the DARPA Sub T challenge. It's a very like robust machine that goes over rough terrain, basically. It's like a tank type robot. And then this Husky has a little arm built onto it. So my question is, what are kind of the requirements for the motors in the wheels of the Husky and the motors in the arm? Oh, yeah, but also like specifically the motor itself. Like that, I feel like that's more of like a wheel or a system requirement. But like, yeah,
It does.
so like,
Yeah.
you mean like kind of high torque? Yes,
Yep.
I agree.
Yeah.
Yeah, yeah.
Yeah. So what type of motor would you think? Yeah, servo could definitely work.
Servo would work.
What's another maybe like another option?
Perfect.
Yeah, so
Yeah.
step motor would be great.
Okay.
Uh,
What about the wheels? I'm gonna guess on what kind of motors those might be.
yeah. So yeah,
Here in DC,
yeah,
yeah.
DC like brushless or brush. So like I don't know specifically. Do you know for specifically with this?
They use brushless DC
Okay.
motors, but you could definitely just use brush DC
Yeah.
motors.
I've never like
It would almost definitely be cheaper to just buy a new DC motor.
yeah. Oh yeah. No, yeah, no. I don't think repairing them is like would be fun. But
No.
yeah.
Yeah.
I think small DC motors just replace it. Big things, yes, you would probably
Yeah.
rework it potentially. Or I think some companies you can send them in and they'll refurbish it for you, especially bigger motors. But oh, so like you mean like small ones, like like six volt DC motors are like like maybe under $10 kind of thing. Like Pololu sells geared motors that I think are like $5, $6, things like that. But it really comes down to how much torque and how much like you need like how big do you need the motor to be? Obviously, it just this cost scales with the size of it is really what it comes down to. Or maybe if it's some specialized sort of thing. And like brushless motors are generally more expensive. They're more complicated, right? There's more engineering that goes into those systems than a brushless motor.
And we'll talk about that right now.
Yeah. Okay. Okay. All right. Feeling a little calmer now. I thought I left the van key. So I was a little stressed out when I first started this talk, but we found the van key, so we were all going home. Okay. So now Alex has talked about kind of like what motors and actuators we could use in our systems, but really we need to talk about how do you actually go about driving them and picking out the systems that are going to accomplish that motion. And so if you took the PCB workshop yesterday, you got to build a little H bridge and design PCB for an H bridge. But driving DC motors is like cake. It's like the simplest thing you could possibly do in electronics. It's really nice because all you need is equivalently four switches. And you have a motor that you connect in the center of this kind of H bridge, and when you turn on these two diagonal switches, you can put current through this motor, which causes it to spin in one direction. And if you turn on the switches in the other direction, you get the motor to spin in the opposite direction. And the reason we use transistors instead of like toggle switches or something to do the switching is you can use a computer or a microcontroller to actually do the switching on or off or reversing of the polarity. So inside the Husky robot, there's like giant H bridges that they use to do this. So typically, the size of your H bridge is just going to scale with the size of your motor almost directly. Here's an example of a little. If you ever just want to buy an H bridge, like commercially, Adafruit has them. You can just buy them online. You don't have to necessarily have to make it unless that's something you really want to do. But controlling these are really easy. You just need a microcontroller, like general purpose input output. You can do PWM, for example, if you want to control how fast the motor's spinning. If you just set these switch on and this switch on, for example, the motor's just going to run full speed. But if you toggle this on and off at a variable duty cycle, so like a certain amount of time on or off, you can control the speed of this. And you can buy these, you can buy them in modules. You can buy them as integrated circuits, like as an H bridge itself. Oh yeah. So like the physical size of this, like how big this thing is, um, the more current, basically, the bigger the motor, the more torque you want, the more current it's going to go through these. So the physically bigger your H bridge needs to be in terms of the integrated circuit or the transistors you're using. So if some people are using like DJTs in the PCB workshop yesterday, they're really small. Those would be able to drive like a very small motor. But if you want a Husky, you're going to need like these massive MOSFET transistors, which are like big. You're probably gonna have to heat sink them, so you have to worry about thermal regulation, things like that. But if you're just doing like these little dinky motors like this, you can basically get away with anything, and it will work. But it's a very simple circuit. You basically just need four components to control the direction of a motor. And yeah, anyone have any other questions? Does that make sense for the most part? We're going to talk. Yes. Sure. Yeah. So, like for example, if you wanted more torque out of it and you wanted to draw lower current, then you could potentially gear it such that you're getting more torque out of the motor, but you only need to put a little bit of current in to get that same. So you can definitely do things mechanically as well to make your life on the electrical side easier. Um, but Yeah, generally the faster the motor's spinning, the less current it draws because there's this what's called a back EMF. We don't have to get into the detail, but basically the current goes down. So if you're running really fast, something like a crop on a plane or something, you probably don't need a massive H bridge that can handle a lot of current. But if it's like husky wheel, where it's like you're going over boulders and there's a lot of torque, there's gonna be a lot of current going through that motor, and you're gonna need something that can handle. So yeah, okay. If you want high torque, high speed, well, so I mean, it's there's a this is a science space is like pretty big, right? Like there's no right answer to it. Um, but if you want high speed and you want the low torque, you're pretty much going to have to design for a low torque case. That's going to dictate the size of your transistors, right? Because current is going to dictate how much heat is going to dissipate through those, and the size to be able to hit the channels in those transistors like need to be big enough to handle large amounts of charges going through it, basically. And if they're really small, that low torque case, you're basically going to burn them up. They'll handle the high speed case, but they won't handle the case. So I think basically you'd be stuck, or you'd have to have some sort of like anyway. This is supposed to be a quick slide, so let's go on. Maybe I mean we have time, but so okay. So servo again, super easy to drive DC motors. Driving servo motors even easier. Okay, you you literally these things have all the hard electronics and control systems inside of them. So really, you just need to supply power. You supply a control signal, which is a PWM signal, which you vary the duty cycle of that. That duty cycle gets encoded the position of the motor or how fast or the direction the motor's spinning and how fast it's spinning. But you just need to connect this to your microcontroller, and the red is connected to your power supply. So it's really, really easy to control. And then you just need to run software. And there's tons of Arduino libraries if you want to go out and not have to do this yourself. But these things run off 3.5 volts or 3.3 volts for the logic typically. And then you need like 5.8 to like 12 volts to power the servos. So if you're building like an RC plane or something, you need to make sure you have at least like 6 volts available on the vehicle. And then really just need a microcontroller to drive this. You don't need a special driver, which is nice. And if you're driving a lot of these, my favorite is the NXP like IC, and it just can drive 16 servo motors simultaneously. So that's always an option if you want to drive a lot of servos. If you're making like a robot, like a spider robot or something that has like a ton of them. Does anyone have any questions on that? Pretty straightforward. Cool. All right. This is where it gets complicated. And we're going to spend not a ton of time on this, but so brushless motors, they don't have brushes. So you have to actively change the current signals that you're driving into these motors in real time to get them to spin. So unfortunately, there's like now three terminals instead of two. And what that means is you have to create these complicated time varying waveforms that basically turn on, create electromagnets inside of this to get to spin at various speeds. We're not going to talk about that. And if you look at this diagram, it's like, wow, it's kind of complicated. Like I have to turn on this coil and this coil, but I have to turn on this coil. Don't worry about it. Just buy yourself an electronic speed controller. That is going to make your life a lot easier. So these are commercially available systems that are designed to drive a DC brushless motor. And the reason why you don't necessarily like you could spend a PhD on designing this because not only do you have to drive the current, you have to sense the voltage coming back from the motor in real time to close the loop to vary the speed. So all you need to do if you want to control a DC brushless motor with an electronic speed controller, is you buy this on Amazon or on Hobby King or something, and then you supply power, typically 12 volts to like 36 volts, depending on how big this motor is. And then you just need a PWM signal to basically tell the motor to go faster or tell the motor to go slower. But that will just make your life a lot easier. And any kind of turnkey brushless motor driver is like probably what I would recommend. There's a lot of other brands that make them. Does anyone have a favorite? Does anyone use speed controllers? No? Okay. Well, they're great. Yeah, you really should try it sometime. But that's kind of the idea. So just get a speed controller. Don't spend your PhD designing the system. Not recommend it. But they're widely available commercially. Stepper motors. Okay, so stepper motors again, these are precision control sorts of devices. Use them in 3D printers. Marshall's using them in his jellyfish, like fish tank. To what are you doing? Are you using it to control the motion of a fin, right? Or like Yeah, so you need kind of precision control to do that and repeatability. So Marshall and I actually just went through this exercise of picking out stepper motor drivers. And so just like a brushless motor, it's really complicated how you have to control the currents going into the motor to step it accurately. And so you can spend your whole PhD designing circuitry that does this, or you could just buy an integrated circuit to do it for you. Um, and all you have to do is supply power, uh, hook up the two coils that are inside this stepper motor, and then on your side, as like the software engineer, you just have to control it with two signals: a direction signal to tell it which direction you want to go, and a step signal is to tell it to step one step. So it's super simple, and that's what I would recommend using. Um, to power these, you usually need like 8 volts to 36 volts. So depending on, I think Marshalls were like 24 volts or something. They're 48. So those are like honking huge motors. Like these things draw so much power. But the nice thing is he was able to control it with an Arduino just by using the step and direction and enable signals, which is like a super easy interface. James. Also allowing steps. Yeah, so like you can definitely get I think this one, for example, yeah. So this one they have kind of like this little interface here where you either pull these signals high or low, and that sets the how much stepping you do. So if you're like doing a 3D printing sort of thing, maybe you need like 1/16th of a step. So basically it's just the resolution that you have for stepping. But yeah, you can do these with almost every commercially available brush or stepper motor drive. And if you need some like a medium size, not like massive stepper motor size, like the SparkFun Big Easy is a nice driver. You can just buy off SparkFun. Adafruit has them, but that's kind of the summary. Does anyone have questions about stepper drivers? Um, yeah, if you wanna learn about the details, it gets complicated real fast. But the summary of motor drivers is what motor are you using? Okay, decide that. And then Google and use the corresponding driver that goes with it. Okay, it's pretty straightforward. Don't use an H bridge with a brushless motor. Don't use a stepper driver with a DC brushed motor. Okay, this isn't rocket science. So we're gonna go through these kind of quick, but we're gonna talk just about some basic kind of sensors on robotic systems, and then we'll kind of go over a couple of examples of like how you would create a system based on some specifications. So again, like you can just throw a bunch of sensors on your system, and those might not be necessarily applicable to your direct what your use case is. So you really have to understand like what am I trying to do? Am I picking berries? Am I cutting lawns? What am I actually doing in this use case? Because that's going to also add to your cost. And you want to make sure you're getting the information that's relative to the application at hand. You have to understand your size and weight constraints. Are you building an insect scale robot like Alex and I, where size, weight, and power is like super important? You can fit nothing on it. So maybe you have to like design your own sensor, for example, instead of buying something off the shelf that just doesn't fit. And then how accurate do you need these things to be? Like if you can get away with like, oh, I just need like a couple of centimeter precision with my time of flight sensor or my ultrasonic sensor, that's going to help you get really much cheaper sensors and also help inform your decisions. And then the environment, like I think a lot of times I don't think about this, but because we're operating in a lab, but like what if you have to go to a place that's like cold versus really hot in the desert versus like what if there's really bright sunlight in some location or it's really cloudy? That's going to also impact your decision because like camera sensor, for example, might saturate if it's super bright and sunny out, or a time of flight site sensor which uses infrared, like that might get washed out if you're using it in really bright sunlight. So for example, like a quadcopter, it's generally we'll say like user controlled for some systems that are not autonomous. It's going to be outdoors, so you don't know exactly what the environment's going to be. It's unstable, and you're going to generally need really high accuracy sensing because you need to be able to uh, uh, be controlled and stable. And then versus the Husky robot, you might need like visual navigation and slams. You might need some sort of depth sensor, RGB camera, in order to be able to detect objects, things of that nature. Has to be potentially like autonomous, like on a naval, for example, where we have to think cavalries of Dark Challenge. So this is inherently stable. So like you might need really high accurate menus for doing sort of like orientation and things like that. So you got to think about kind of the trade-off between those. So we'll just go quick through this. Time of flight sensors, also referred to as TOFs, are kind of like poor man's LiDAR. These are generally I2C sensors. They're really low power, but they operate by just sending out some photons. They hit your target, and then those photons come back, and you measure the time difference between that to calculate how far away your object is. Unfortunately, ambient lighting conditions do impact this. So, like if things are really sunny and bright, or the object you're shining at doesn't reflect very well or absorbs a lot of iron, that's going to change your reading sensitivity. But these are cheaply available. They're small. You can buy them as ICs. So I use these a lot on different systems. So they're pretty cool, and they sample pretty fast. So like you can go over 60 to like 100 hertz. I think pretty much everyone has seen an ultrasonic sensor if you went to especially if you went to the embedded systems workshop yesterday. These work by sending out a ping of ultrasonic 50 to 100 kilohertz sort of signal, and then that reflects off an object and comes back. So you don't have to worry about light interference with these sensors, but you do have to worry about like the softness of the material, the shape. So there's kind of orthogonal noise and things that impact the performance. So combining, for example, sensors together might be a way to improve robustness. Where one sensor fails, you can pick up and use the other. These again are like they can sample, between 30 and 100 hertz. Companies are starting to make now integrated circuits, not just like these massive, like kind of hobbyist sort of ultrasonic sensors, but you can get stuff that is like 3 by 3 millimeter and can mount on a PCB, which is really cool. So you can like array these things if you wanted to kind of make like a phased array and reconstruct things in 3D. So there's stuff that's coming out that's pretty cool, I think, in the future. But who knows? This might get like, you know, supplanted by the radar systems that people are coming and using nowadays. Then last but not least, obviously, Jacopo talked about camera sensors at his talk the other day. Cameras are like super popular nowadays, especially for object classification. If you want to do some sort of flow-based sensing. A lot of algorithms rely on these for navigation in the environment, and you can get these at all sorts of different sizes and different video interface protocols. So we don't have to spend a ton of time on this, but for example, you can get systems that are down to milliwatts, and this is something we're trying to integrate into one of our insect scale robots. But this thing weighs like 150 milligrams, which is like 25% of our robot's weight. But it is cool nowadays that you can get systems this small, but you can also get them to be massive and really high resolution. But they do scale down to the sizes that you could use with a microchip, for example. We're just gonna skip over this because okay. So everyone knows. Does everyone know what an IMU is? I'm guessing. Yeah. Okay. So pretty scary. Okay. So let's just go through a quick example, and I'm gonna engage the audience here and ask you guys some questions. But imagine we have a quadcopter and we're trying to do some sort of autonomous navigation in an environment that's unknown, right? So we're going to need some way of detecting obstacles. We're going to need some way of detecting how far the ground is away from us, and we're going to need a way to, estimate our orientation. Does anyone want to guess maybe one sensor we could use for obstacles and ground sensing? Yeah, you could use a camera. Sure. Yeah, ultrasonic. So ultrasonic's definitely a good option. Uh, what's the one thing that people haven't said? Yeah, yeah. So the time of flight sensor, like they've used these on crazy flies, for example, to do fully autonomous navigation. They're super cheap and they're like lightweight. You can get them like they're like literally this big. So then some of them do like 60 or 16 by 16 like arrays, so they can do like a poor man's kind of depth sensing. And then orientation, I think, is pretty obvious. It's like an IMU, right? So having all of these sensors on a system enable you to have some sort of fully autonomous system that can navigate by itself. Okay, so let's just talk real quick about some. So now that you basically picked out sensors, you picked out your actuators. One of the things you kind of have to decide on is how am I going to process this data and how am I going to do all the control. And so a lot of times, from my experience, that is dictated by what type of sensors you're using, how much data those sensors are generating, and what kind of interfaces those sensors need, right? So and I'm going to tell you, like, you don't necessarily need to pick like a microcontroller or a single board computer. You can pick both, for example. So a lot of times you're going to have sensors that might be really low level, and they'll need like I2C or SPI or that's integrated circuit communication or like SPI, which is a serial parallel interface protocol, which allows you to communicate between like microcontrollers and sensors. Um, but we're going to first just talk really quickly about some single board computing options. So, for example, the NVIDIA Jetson is kind of an old system at this point, but they have many, many flavors of this. These are systems that if you need a little more computational power, these can handle, at least some parallel processing. They have usually 4 or more cores. and they're kind of unfortunately a little bit power hungry. But these are kind of higher speed systems compared to microcontrollers. They have a lot of RAM and they have a lot of flash. So if you need to like buffer up a number of frames for your computer vision algorithm, you can actually do these on these systems. And generally, you can use Python or these higher level languages that get you away from C++ or C. That's going to be what you're going to need to write on microcontrollers in general. But the downside of these systems is like obviously they're bigger. There's much higher power requirements, which we'll talk about power supply in a second, what that's going to mean for the rest of your system design. And there's usually a little bit higher latency when you have an operating system operating on top of your hardware versus like a microcontroller where you can write bare metal code, which is just going to talk directly to hardware and there's no overhead associated with it. Uh, and yeah, does anyone have any questions on that? Everyone's seen like a single board computer, right? I think everybody's experienced Raspberry Pi at this point. Yeah. Okay. And then on the other side, if people aren't familiar more with these lower level sort of processing systems, microcontrollers are really just like very hardware oriented processing units. So they usually have one or two cores for processing, just running instructions, programmed in C. And then they have a lot of hardware sort of related peripherals for interacting with like low level sensors, controlling different interfaces like motors. But these you can get in a wide range of capabilities. So 32-bit is kind of like the industry standard at this point. You're not really seeing many 8-bit or 16-bit systems. Why would you use that? But you can get systems that are like super fast, like 600 megahertz on the teensy side, if anyone's used a teensy. These are kind of the systems you throw at it if you're like, I don't know how fast I need to execute this algorithm or how fast I need to sample something. I'm just going to use a teensy and just like know it's going to work. But if you are more resource constrained, you might use kind of these lower end systems, like the Nordic Bluetooth NRF 52840, which is like very popular for most IoT kind of systems, but it's very low power, but just doesn't have nearly processing capabilities. But again, these systems really low power. You can get them in like 2.5 by 2.5 millimeter packages if you need something uber uber small, which is what kind of Alex and I needed on the free fly robot that we're building, which is our little flying robot. Very low latency, real time sort of stuff. They have a lot of rich peripherals on the outside that you can use to talk to cameras, talk to sensors, or things of this nature. But again, you have low speed, low processing capabilities compared to the single board computers. Like you have to write really efficient code and you have to write really low level code to do this, which is not always fun. It can take a lot of time. When your PhD is to get a paper out, and I spend a lot of time writing the code. And the hardware interfaces, like the peripherals, you can spend literally like a month writing a driver for the peripherals. If anyone's experienced that, it's not fun. Good documentation is very. Okay, so yeah, we'll go through this. Yeah, James.
Programming, do you have any experience of like VLC versus MicroPython?
My feeling is like MicroPython is like it's not very good. I tried it once. It's really, really for like hobbyists, I think. Or if you're doing some sort of like experimental setup where you just needed to like do one really simple thing and you don't want to spend the time like setting up a tool chain to program the microcontroller, that's like an option. I would just never use it in anything serious. Uh, yeah, like Arduino, there's a little bit of overhead writing with their kind of code base because obviously like they handle a lot of the complexities for you. But like, so my kind of thing in our lab is like anything that is kind of workstation related, anything that's going to collect data, anything that's not going in a robot is going to be Arduino based just because it's super fast to get spun up and running. But then anything that needs low power, needs precise control, like deterministic behavior, I'll write in C and I'll use generally whatever the vendor who makes the microcontroller. I'll use their kind of hardware abstraction language to write the code, so I don't have to like write at the register level because I just don't have time to do that necessarily. It just takes too much. Um, yeah. Any other questions? Okay. Yeah. So picking a processing unit. We'll go through this pretty quick. Again, sensor complexity, how much data, kind of stuff. Algorithmic complexity, how fast you need to be able to process data, how fast you need to execute your real-time controller, for example. Your system dynamics are going to play into this. Like if you have a quadcopter where you need stability and your system is inherently unstable, you might need something that's really low latency to make sure you're going to have all your pulls in the left-hand plane and be stable. And then again, like if you are building a sex scale robot and you can't obviously put a Jetson Nano on it, like size, weight, and power is going to be a huge driver as well. Okay, so we'll spend a little more time, supposed to spend less time on that and more time on this, but here's a real world example of like a block diagram of a real system. So if anyone's played around with the Crazy Fly, um, these are little flying quadcopter open source systems, and they use brushless DC motors to drive the propellers, and they inside use an IMU for basically doing orientation and sensing. And this is a system you really need low latency, you need simple sensors, simple control, and low level cogs. So what they did is they ended up using an STM32 M4, which is a pretty high speed microcontroller with a lot of hardware peripherals, but it doesn't have like a lot of RAM. So you have to be really efficient with the code you write. But this control loop to be able to stabilize the platform and maintain attitude is like super fast and super low latency. So that's kind of the reason why they went with this like high speed microcontroller that has an FPU, a floating point unit inside of it, and has a pretty decent processing capability. But say you want to be able to like navigate through the environment and do some sort of like machine vision navigation or object classification, and you can handle a little more latency, for example, they have what they call an AI deck, which is a system that sits on top. So once you know you have a stable platform, this board on top can basically be a little bit slower and do a little more complex sort of computation. And so the first thing is they want to have a camera to be able to see the world. This camera has parallel interface, which is a low level interface. I don't think most of the Jetson necessarily have these capabilities. So what they did is they picked a GAP8 processor, which is like it's a RISC-V processor. If anyone knows what RISC-V is, open source architecture, uh, and it's super fast, but it doesn't have a lot of RAM. Okay, so like if you want to buffer up a couple of frames to do like optical flow detection or do some sort of machine vision edge detection sort of algorithm, you need to be able to buffer up like a couple of frames at least. And so they use a really high speed bus interface to communicate with an external RAM chip on the board. And so that allows them to take imagery in and store it in here and then actually do mathematics on it in real time. And so that's one way you can get around the bottlenecks of the limitations of microcontrollers and not have to use like a Jetson or something with a lot of RAM. And then last but not least, they want to be able to stream this data back to like an Ubuntu machine or something so that you can actually watch video of the system in real time. And so they use an ESP32, which is, yeah, Harry.
Speed of the bus.
This, I think it's probably in the order of like 650 to like 100 megahertz. But it's what a quad bus, spy bus. So most people probably worked with spy buses, but a quad spy is just four lanes of data as opposed to one. So you're getting for 50 megahertz rate, you're getting 4x the data transmitted across. So it's just way quicker to transmit. You can transmit megabytes of data across this bus. So that would allow you to basically get real time access to this memory out here for processing. So that's kind of cool. Like you can actually make, and this system draws like tens of milliwatts of power versus like tens of watts for a Jetson. So that's kind of a cool thing you can do if you need that capability. Okay, so we'll go through this kind of quick. How many people here have like how to pick a battery for a quadcopter system? Hari? Okay, or like just a robot system in general. Like you're like, oh, how big of a battery do I need? Okay, so for me, it was always kind of like a mystery of like how you go and pick this. But I think the first thing you have to understand is like, okay, how long do you need this thing to last? What's kind of the power requirements of your system? Like, is this a quadcopter drawing amps of current, or is this like a piezoelectric flying insect that draws like milliwatts of power? So a lot of times when you get a battery data sheet, you're going to see like this really complicated sort of table. It's going to give you a ton of information. The really important thing to pay attention to is what the operating cell voltage range is. That's going to tell you kind of what the range over when this battery is discharging, the maximum and the minimum voltage you're going to get. And that's going to be important for when you're designing your power supply systems later. And then understanding the specific power and the specific energy. Generally, you want this number to be really high because that means you need a small battery for the same amount of power or the same amount of storage capability. And then you also want to understand what the max discharge current is. And so we'll talk about this in a second, but they give it to you in this C value, which basically you take this number and you multiply it by your milliamp capacity. So like say it's a 500 milliamp hour battery, You multiply that value by this to understand what the maximum current draw your battery can consume. And we'll go through a real example right here, for example. So imagine you have a quadcopter and it draws, it's this much weight, it needs this kind of a voltage, has a max current, has an average current, and you have a run time that you have to be able to run for a certain period of time. And so to go and pick a battery for this, we would first basically calculate the number of hours that the system needs to run in hours from minutes. And then we know what the average current is. So on an average kind of flight of hovering, for example, you would do your 22.2 amps times 0.61 hours. And that's going to say that we need a battery that's roughly 3,500 milliamp hours. So let's just pick the next biggest capacity that's available, which is like 5,000 milliamp hours. We're not so worried about the size or the weight can be pretty big. So we'll pick something that's a little bit bigger. And then the discharge rate. So we know that the maximum current is going to be 60 amps. That's a huge amount of current. Um, and we know that our capacity is 5 amp hours. So if you do 60 amps and you divide that by 5 amp hours, that tells you that we need a C rating of 12. So we need to be able to discharge the battery 12 times its capacity rate. And so as long as we have a 12C or higher battery, we're good. We can handle the amount of current draw. And then last but not least, the voltage. This is supposed to be 14 to 15. Um, we need 4 series cells to get to that voltage. And that's because 14 divided by the nominal cell voltage of a lithium ion battery is 3.7. And so that gives you 3.78 cells. You can't have a half a cell or 0.78 cells. So round up to the next one. And that's going to get you over your voltage minimum requirement. So what we picked from all of this is a Turnigy graphene. They don't actually make this anymore. It's just an example, but it's 5,000 milliamp hour. It's 4 series cell. That's what the 4S stands for. And we've absolutely crushed the current requirement. We only needed 12. We got 45 on this thing, so we're good. And it can do 9 DC peak, so 90 times what the capacity is. I'll let you do the math for that. Okay. Does that make sense? Yeah.
Like, it's like salts in like a normal battery.
Yeah, so really it's gonna come down to basically always pick a lipo. That's kind of what the industry standard is nowadays. But if you really wanted to understand it, you would have to understand what is the voltage requirement for my system, and does that fall in kind of like the nominal voltage range? There are trade-offs with specific energy and specific power. So if you look down here, like nickel metal hydrate batteries, for example, those are pretty low specific energy. So like you need a bigger battery to have the same amount of capacity as a lithium ion. So to me, it's kind of like, why would you pick like this is just an older technology. It's a lower density. So unless there's some specific reason I'm missing inside of here, uh, like maybe they're really good over temperature or something like that. But I would say unless there's a really unique application that you have for your battery system that would require using a different technology, generally it's going to fall into a lithium ion technology. And then you're just going to pick the size of the battery based on like how much current you need and the voltage. So
Do you have any personal preferences on lithium LiPo versus lithium ion versus lithium ion phosphate?
I mean, so I personally I don't. I've basically just picked like lipo batteries for the most part.
My
Most
understanding is that lead acid is bad.
yeah.
Lithium iron phosphate is safer.
Yeah, I think there's the high safety ones. Yeah, I think that's yeah. So I think those generally don't burn as easily. So like if you were doing like a firefighting robot or something, or maybe some a certain that'd probably be a really bad situation. But yeah, maybe a system that's going to be in higher temperatures. That might be the option to pick. So
Sorry, I didn't mean
yeah, no, you're totally good. Yeah, no, exactly. So there's other reasons for picking different chemistries of battery, but in general, I would say start with lithium ion, and then from there, if you have a very unique special case, like this is going to go in a pacemaker, or this is going to go in something that cannot fail, then maybe you need to go to like a different type of chemistry. But yeah, okay. Okay. So does anyone here know what a buck regulator is versus a boost regulator versus yeah? Okay. So we're just gonna go over this really quick. So there's when you have a battery voltage in general, or you have a power source, you generally need to regulate that voltage down to something that you can actually use to drive your motors or drive your sensors. Like you just hook up your battery to your Arduino, it's gonna fry it. So we need to step down generally that voltage or step up that voltage to a value that's going to be compatible with the system that we need to power. So the first type is what's called a linear regulator. And so this regulator operates basically a transistor in a linear mode, and that transistor just acts as like a variable resistor. So you apply voltage to the input. This has a little control loop inside of it, and at the output you get a fixed regulated voltage that's very clean, and it steps the voltage from a higher voltage down to a lower voltage. So these are really common. You'll see these are like on an Arduino for generating 5 volts for the Arduino. They're really low noise. That's kind of one of the key things to take away. Uh, and the higher power you need, the bigger this thing is physically going to be. Physically, you need a bigger linear rate. And so that's on the linear side, and these are really low noise. But on the switching, what's called switching side, you have systems that basically use transistors to switch on and off at a really high speed to either step a voltage down or step a voltage up. So we have what are called buck converters. Buck converters step voltages down, but they step it down using switching regulation and inductive elements. We're not going to go into all the details of that, but this does it really, really highly efficiently. So if you have to step down a large amount of voltage and you want to do that with like high currents, for example, a buck converter is going to be the way to go. Boost converter is the opposite of buck converter. It lets you step a voltage up. So say you have a low battery voltage, like a single cell lithium ion, but you need to drive a motor at 6 volts. You would use a boost converter to step that voltage up to a high enough voltage to drive that motor. Uh, and that's really your only option if you have a higher voltage besides what's called a buck boost for converter. So this is like the best of both worlds because it just no matter what voltage you put at the input, if you say I want 5 volts at the output, it's going to maintain 5 volts. So even if your battery say starts at 7, but it's decaying down to 3, it's going to maintain 5 volts at the output. So buck boost converter is a little more complicated. The electronics are more complicated. There's usually a few more parts, but that's going to no matter what the input does, it's going to give you a solid voltage output. And these switching systems, the thing to remember, super efficient, noisier. So in general, and when I say noisy, that's electronic noise, not audible noise. And they do generate some audible noise, but they're very much noisy in terms of like if you were to measure with an oscilloscope, you'll see a little more ripple. The control system that controls it just isn't as tight as a linear rate. So I guess we'll just kind of skip through this, and you can look at this later. Um, so yeah, we'll go through this really quick. So imagine you have a quadcopter, you have brushless DC motors which draw a shit ton of currents. Uh, those you're probably not going to want to regulate, especially if you have a battery voltage that is right at the amount of voltage that the motor driver needs. So I would just drive it directly into the motor driver, direct to the motors, and there's no efficiency loss there. You're not going to dump any power into converting this to a lower voltage or higher voltage. But say we have a radio that we want to have really low noise because we want it to be able to transmit a long distance. And we have a flight controller with a sensitive IMU. Probably a way to go about this. And these draw like a little bit of this draws a decent amount of current. This draws a little bit of current. One way to get low noise is to use a linear regulator. There's no switching going on inside of this. It's a linear system. That's going to give you a really nice clean voltage. So that can give us 3 and 5 volts. But how do we get from this really high voltage here down to 5 volts here without destroying our efficiency? Does anyone have any idea what we could use to maybe step the voltage down and maintain high efficiency? What's that? Exactly. So we could use a buck converter to go down to like an intermediate voltage. So it takes the battery voltage down to maybe like 5.5 volts. Now we're only dropping half a volt across here and a little bit over a volt here, and we're getting 90% efficiency. So that's an example of a system that like you could very readily get the best of both worlds. So low noise, high efficiency. And then these are for reference later if you want to come back, but this kind of shows you the breakdown of the pros and cons of each type of system for voltage regulation. And I'm going to hand over to Alex finally. So,
All right, so moving on to controls. So yeah, this is a nice little picture that Brian Douglas, famous kind of controls engineer influencer, made. And you can see there's a million topics in controls, so I could never even come close to covering all of them in this presentation. We'll be focusing more on this area of the graph, so that your more typical controls algorithms. So to start, we have a PID controller. So hopefully everyone has at least heard of a PID controller, maybe used one. And this is kind of the bread and butter for controls. You're gonna like somebody in the industry presentation said they just use a PID controller on their lawnmower, I think it was.
Yeah,
So yeah, it's a very useful, very ubiquitous controller. And it's nice because you basically just tune the values to whatever kind of you want. So yeah, good at a lot of things. And then this balancing robot maybe uses a PID controller to help it balance. And then a line following robot, this is like a classical example of a PID controller. All right, so moving on to a more kind of complicated controller, we have MPC. So this is much less simple, but it's still nicely stable and robust, and it has a lot of applications. And so this works by basically the robot knowing its state and predicting what state it will be in the future, and then changing its inputs based on that, and then it predicts the state again. So it keeps kind of thinking about where it's going to be in the future and changing its motor control inputs based on that information. And so, for example, the spot robot, uh, I don't know if the current spot robot actually uses MPC anymore, but definitely the original spot robot used MPC. So kind of more complicated robotic systems will use MPC. Then we have reinforcement learning. So not simple, but very useful. You can kind of teach the robot basically to do something. So you have a neural network that you train, and then it can accomplish a task. So I gave this example of this robotic arm. You could, for example, use reinforcement learning to train a neural net to have this arm. I don't know, go get something from the fridge for you if you want like Coke instead of Sprite or something. It can remember Coke, and then it'll get that for you. I don't know. All right, so Kalman filters. This is kind of a different region of the controls map. So this is more in the state estimation area. There's a bunch of ways you can do state estimation. There's also what's called a complementary filter. That's kind of more simple version of a Kalman filter used for processing IMU information. But the way a Kalman filter works is basically you have sensor measurements on your robot, and then you have where the robot thinks it is, where it is. And then as the robot does stuff in real life, those things kind of diverge. And so the sensors might think that you're in a different location than where the robot thinks it is based on like what inputs it's given to the sensors. And so the Kalman filter reconciles this information and provides you with a more accurate state estimation. And so that's what this drawing basically is showing. And yeah, this is very ubiquitous. Like it's used in all kinds of different robots for having a more accurate estimation of your state. So here's an example. We have the spot robot. So what kind of controls algorithms do you think are going to be used on the motor level at spot? Sorry? PID, yes. They probably use PID control or something similar, maybe LQR, something like that. And then on the system level, so this is going to decide like where spot's going to go, what kind of stuff it's going to do, what kind of algorithms would you think are is there? Yeah. Did someone say reinforcement learning? Sure. Okay.
Yeah.
Yeah, so I basically put all of them. Like Spot's a very complicated robot and it probably uses all of these things. So yeah. All right, moving on. This is our last topic. So mechanics. And this is a very kind of broad topic. And so it's less kind of structured like the previous topic. So I'll just kind of give some general tips on how you want to design like the mechanics of your robot. So one very important thing that people often forget is that you want to create a model for your robot if you can. So use free body diagrams, use M equals MA, use like torque propagation, stuff like that. Compute like what the forces are going to be on your robot, and that will help inform your design. You can look at system dynamics as well, kinematics, forward and inverse kinematics, if you have like an end effector robot, and also linkage design. If you want your robot to have some kind of complicated motion, you can look at that. All right, so physical modeling. This is just a table I created with five different CAD softwares. So I use SolidWorks. Art uses Fusion, so I think that's why.
So I'm an electrical engineer and I don't know how to use softwares.
So you can come back to this later, but basically, I think SolidWorks is great for. It's the best for solid modeling, and it has a lot of great add-ons as well. Onshape is becoming more popular. Has anybody used Onshape? Yeah. Is that what they're teaching now?
Not really.
No, it's still SolidWorks. Okay, I know some universities are kind of moving towards Onshape. It's nice because it has great version control and it's all in the cloud, but it's also in the browser. So
Yeah.
Angie told us not to recommend that to you. But
And you can
it's
use Python for Fusion
it's
scripts.
true, yes. Fusion, I think Fusion is sort of the better version of Onshape because it has that version control, everything's stored in the cloud. SolidWorks is great for if you want to do any complicated solid modeling or analysis. Siemens NX is basically the more expensive, fancier version of SolidWorks.
Do we have that at CU or
I don't think so.
no? Okay. Yeah, don't use that.
Some companies use
Unless
that.
you're forced to.
There's also a million more. There's like Rhino, Creo, there's a bunch of SolidWorks. And then this is kind of comparing some different analysis tools that you might use. So we have CAD tools. There's also finite element analysis and topology optimization. So if you want to optimize your designs, if you want to like produce weight, something like that, or if you want to look at system level dynamic analysis. Somebody was talking about Ross and Gazebo yesterday in the industry thing. That's great for if you want to model your robot, if you want like a digital twin, something like that. NTOP is nice for NTOP and Abacus both good for optimizing your designs. And then these things in the middle, like SolidWorks, Siemens, they can kind of do it all. But if you want, for example, great analysis, Abacus is going to be the best. But if you just want something simpler, SolidWorks is going to be nice. All right, so purchasing components. There's going to be a lot of things that you don't want to or don't need to design. Like you don't need to design your own bolts, fasteners, stuff like that. Propellers for your drone, unless you're doing a PhD on that. So you're going to want to buy a lot of the stuff. And so these are just some examples of typical vendors. So McMaster is great for fasteners and kind of random stuff. Same with Amazon. And Mouser and DigiKey are kind of two major like electronics components manufacturers. Adafruit is good for integrated circuits and microcontrollers.
And like modules too, because you can get
Yeah.
PCBs like that you can test out immediately day one, and they have every single board has a library of code associated with it.
Yeah. And then the ITLL, so for people who don't know, there's a lot of kind of free stuff you can get at the ITLL. So you can go.
If no one sees you, take it.
Yeah.
No.
All right.
Oh, and actually, can you just go back real quick? Yeah, and then also the really cool thing is like Shikar, for example, has all of the step files available. Like, so you can just if you're building a robot, if you get stuff, even if you don't buy it from McMastercard, you can like literally get almost your entire robot design, like just downloaded and into Fusion or SolidWorks. There are add-ons too, actually. Like in Fusion, like you literally can just navigate and browse to McMastercard and insert it directly inside of Fusion, which is kind of nice.
Or you can just download it. Yeah, so for if I'm gonna do stress testing of individual components, I'm gonna use SolidWorks. Like I'm not designing anything complicated enough typically to use Abacus. Abacus is nice. You have a lot more granular kind of like a lot more choices to make basically. So you can do more kind of professional or interesting analyses on Abacus. ANSYS is also really good for analysis. It's kind of I would say yeah, it's just another great tool. There's a lot of good tools for simulation. SolidWorks is the most simple. So if you just want to like apply a force to part and see how much, where the force like stresses are, then SolidWorks is good. If you want something more complicated, ANSYS, Abacus are both great.
And they're like multi-physics, right? Like
Yeah.
ANSYS is like you can do like electromagnetics and then just see how much heat you're going to get out of your motor and then use that to determine how much like, heat sinking you need. So like you can do like different cross domains kind of stuff. But like SolidWorks, I think it's mostly like you can do some multi-physics or is it?
You can do dynamic analyses, but it's more like focused on mechanics. So
Yeah.
I don't think SolidWorks has any like fluid simulation or heat simulation, but it might be wrong. Yeah, yeah. There's a FEA toolbox. Yeah.
And ANSYS, like there's licenses to the university.
Yeah.
There's also Console, if anyone's used Console, but like that's another multi-physics
Yeah.
engine that's available through the university, but it's kind of complicated.
SolidWorks is very plug and play. So. All right, so design inspiration. So maybe you're designing a robot and you want to just get inspired by other people's projects. So here's some links. I'm not going to go through them, but you can come and click on them later and take a look. There's some cool, like, kind of interesting linkage designs in some of these. And then some design rules with them. We'll just kind of go through this pretty quickly. You want to keep things as simple as possible mechanically. Use standardized components, and also don't use a million different types of bolts. Use like the same one if you can.
Same thing for electronic components too.
Yes, exactly.
Like if you could use the same resistor in your design over and over again, it makes your bill of materials like when you're ordering your board a million times easier too.
Yeah. Avoid over constraining things. Design for manufacturing and assembly. This is important. Like you might design a robot with straight in CAD, and then you realize you can't screw in a bolt because it's being blocked by something else.
Or you can't 3D print it because there's like an overhang that's like super hard to, you know.
Exactly. So yeah, very important. Avoid stress concentration. So this looks like SolidWorks. So this is a simulation you could do with SolidWorks in like 5 minutes. So pretty easy to use. You'd probably want to like fillet this edge to avoid that stress concentration. Include redundancy. People were talking about that all the time yesterday. And then yeah, I guess I included this one sort of twice. But yeah, very important. Make sure you can screw in all your bolts and stuff like that. All right, that's it. That's it with our presentation. So now we have a game for you all. So there are 3 different systems that we made. There's the Spot robot, there's a quadcopter, and there's a fixed wing aircraft. And there's like a little story associated with how the design should be, like what are the important things, and then a skeleton block diagram. So there's little arrows, and some of the blocks just have it'll say like voltage regulator or motor. And your goal is to put the proper component into place and draw the arrows in the block diagram. And we're going to send this to you on PowerPoint because I must have left.
So we're gonna email this to you right now. And like if you want to kind of break up by table, like maybe 2 groups per table or something, like just 2 people need a laptop, and then we're gonna create the system block diagram kind of together.
Links maybe 5 or 6 different things. All people